The topic of the video is orbital angular momentum operator. Orbital angular momentum of a particle of mass m and located at the position vector r and moving with velocity v is defined as L is equals to r cross p, where p is mv. In the components form, if L is expressed as Lxi plus Lyj plus Lzk and the position R as xyz and the momentum P as Px, Py and Pz, then we can see that Lx, Ly and Lz take these equations. And we know the basic commutators between x px will be ih cut, and between ypy it will be the same answer, and between zpz it will be again same answer. But if we have any other combination of these xyz with px py pz, then the answer will be 0. We next try to discuss or prove that the components of orbital angular momentum, which are Lx, Ly and Lz, do not commute with one another. For example, let us take the case of the commutator of Lx, Ly. Then if you substitute for Lx and Ly, the commutator can be written like this. And by using the fact that the commutator of a plus b with c plus d will be ac, ad, bc and bd, we can write even this commutator as a summation of these four terms. And by using the fact that if you have a commutator of a with bc, then we can write it as a commutator of ab and c outside, and b in front, and then ac. So by using this fact, we can write the commutators that we had on the right hand side as 4 will become now 8. 8 terms. And again, by using the fact that the commutator of DE with F can be written as D outside and EF commutator, and E actually towards the right, and then DF commutator. So if you use this formula and if you write all those 8 terms, it will become 16 terms now. And out of these 16 terms, all the commutators are zeros except the ones under under which I have put these red arrows, red bars like this. So these two terms will not be zero, and in fact they actually will give you they have got this term like commutator of z with pz, which is ih cut, and reverse of that, which should be giving you minus ih cut. So we get the summation of 16 terms to this answer. And in fact, if you pull out ih cut factor outside, you will see that it's exactly equal to your ih cut into lz. So we can say that commutator of Lx with Ly is ih cut into Lz, and similarly we can see the commutators of Ly, Lz will be ih cut into Lx, and Lz, Lx will be ih cut into Ly. Therefore, we can say that the components of orbital angular momentum do not commute with one another. Next, we try to prove that the commutator of L square with Lz will be 0. The L square operator can be written as Lx square plus Ly square plus Lz square. So this L square commutator with Lz can be written like this. And we can separate the right hand side into 3 parts. And we can write these 3 also into 6 terms like this. And in the 6th term, the last 2 terms will be actually 0. And the remaining terms have got some kind of commutator of Lx with Lz and Ly with Lz. So we'll be getting these as answers. So if you substitute them and if you simplify, you will see that it'll turn up into 0. So we say that the commutator of L square with Lz is 0, and similarly we can also see that the commutator of L square with Ly is 0, and then the other commutator L square with Lx will also be 0. Next, we try to find out the expressions, or at least give the expressions and eigenvalues. Expressions for eigenvalues and eigenfunctions of operator L square. The eigenvalue equation for L square can be written as L square acting on some function ylm theta phi will give you L into L plus 1 into h cut square into ylm theta phi. And for Lz operator, the eigenvalue equation is Lz operating on ylm theta phi will give you m h cut into ylm theta phi, where these ylm theta phi's are defined like this in terms of plm cos theta functions, and these ylms are called spherical harmonics. And these plm of x, they are called actually the associated legendary polynomials, and they are defined like this. And here m can be taking values from minus L plus 1 all the all the way up till L minus 1 and L. Therefore we can say that eigenvalues of L square uh, are actually L into L plus 1 h cut square, and eigen function of L square is ylm theta phi, the spherical harmonics, spherical harmonic. And then the eigenvalue of Lz is m into h cut, and eigenfunction of Lz is ylm theta phi again. That's it in this video. Thanks for watching.